So I'll begin, let me make sure this thing's working. Yep, okay. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for these students. And I just ask that you bless this class, help us to understand the material we're going over, and just for the students to ask good questions as they have them, Lord. In your name I pray, Lord Jesus. Amen. Okay, so let me put that away. So let's see here. We're on lecture, what is it? 19? Is that right? We were 18 last time, right? Yep. So lecture 19 it is. And so we need to talk more about Euclidean geometry, right? So what is Euclidean geometry? So Euclidean geometry, I mean, the Euclid in it is kind of the key, right? Like that's where we think of it coming from. Who was Euclid? I think we talked about this early on, right? A little bit. So Euclid was a Greek mathematician. You know, he lived before the time of Christ, I believe, a couple hundred years before. And his books of elements have survived, you know, the many library fires that, I mean, if you start reading Wikipedia about different ancient Greek mathematicians, it's kind of depressing because you read about all these books these guys wrote and they're all gone. Like they've all burned up in some fire somewhere in like 1400 or 400 or something. And so despite the fact that these ancients solved all kinds of problems that are really kind of impressive, like Eratosthenes, they talked about last time, estimated the circumference of the Earth to within a couple of percent. He estimated the size of the sun. He was off by about like 30, by like about a factor of 3 or something. But you know, a lot of the things that those guys wrote is just lost, right? And it's, oh well. But Euclid's work was not lost, and it pretty much set the stage for elementary school geometry instruction for quite some time. So Euclidean geometry, the true heart of Euclidean geometry is what's called constructive geometry. So Euclid's geometry, you know, there's sort of two different kinds, all right? There's what I would call constructive geometry. So this constructive geometry is, like it sounds, based on construction. And what do I mean by that? There are really two constructions, all right? There's like compass and straight edge. So compass straight edge constructions, that's really what constructive Euclidean geometry is all about, all right? How many of you had a class of geometry in high school where you did proofs, like column proofs? Anybody? How many did not have a class in high school with like constructive column proof type geometry? How many people don't understand my question? Okay, no, it feels like about 50-50 from where I'm standing. And so it's often people's first experience with proof. And well, I'm personally not a fan because I think Euclidean geometry, you have to work so hard to prove things which are obvious. So I like proofs where you're proving something that's not obvious, and to me it feels like you've done something more, right? When you prove something obvious, it kind of feels like, okay, lovely, but whatever, you know? So that's the one thing, constructive geometry. But Euclid did not just do constructive geometry. He also dabbled, I would say, in what I would call analytic geometry. What's analytic geometry? So this basically is associating numbers with distance and ultimately, you know, we identify points in plane with pairs of numbers like x comma y. Now, I don't think it's fair to say Euclid did so much. In fact, I think it's probably wrong to say Euclid did the second thing. But he was kind of experimenting in that direction in some sense, all right? But, okay, so like, analytic geometry really came into its own. Analytic geometry was only really fully fleshed out much, much later. This came into its own, you know, with the work of René Descartes. I don't think there's that S there. I misspelled Descartes. It's all the fault. I took a class in college called the Rise of Modern Science. It was a history class, and in that class there was a student who used to refer to Descartes as Descartes. So it's forever burned into my mind. So it's why I misspell it sometimes. But anyway, Descartes is the reason that these xy coordinates are called Cartesian coordinates. It's in honor of Descartes, because he was the one who really championed the idea that we can use numbers to represent points, and so then we can also use equations to like describe geometric objects, right? So have you thought about this? Maybe you have, maybe you haven't. How have you guys talked about a line in your previous math classes? Like, you take this for granted, right? You take this for granted, but in elementary school, well, maybe not, excuse me, elementary school, let me not be ridiculous, but in like high school, middle school, whatever, you did things like this, right? You're like, here's the xy coordinate system, here's a line, right? And how did you describe that line? You gave a formula for it, right? What was the formula for a line, generically speaking? Do you remember, like, if I told you that the y-intercept here was 2, and if I told you that if you go over 3, you go up 1, you could tell me the slope was what? Y equals mx plus b, right? What are m and b then? Well, b is 2. All right, I like that. B is 2. The slope is the rise over the run, right? Which in this case is 1 over 3. So the formula for the line I just wrote up there would be y equals to 1/3 x plus 2. All right? This is something I think most of us have done either in like early high school or middle school, somewhere in there, right? And it's actually not that bad, right? Like, this math is not that bad once you get used to it. Now, some of you are like, are you going to test on that? Because I've forgotten all that. And the answer is no. That's not part of this course, right? I don't think you even have any homework on this, right? I'm mentioning it because I want to attract your attention to that. That's how you've been taught to think about lines, right? That's an example of analytic geometry, because we're using an equation to analyze the geometry. And in that sense, it's analytic, right? This is not the way Euclid thought about geometry so much. He thought about it in terms of more based on compass and straight edge construction. So what's a straight edge? It's just what it sounds like, right? It's like a ruler, but the deal is this right here, I would not count as a straight edge, because the bad thing about this right here is what? It's got, see this? 1, 2, 3, 4. It's got a regular measurement and tick marks on it, right? So you can measure along that. That's not a straight edge. A straight edge is just a line with no markings. That's a straight edge, like this up here, right? So let me show you an example of a compass straight edge construction. Now, for those of you who've had high school geometry, this will be like completely unsurprising what I'm about to do. But for those of you who haven't, this might be a little bit interesting. So suppose you have a line, all right? And Euclid also thought about points, so we can think about this as a point, and this is a point, right? So one of the things you can do in constructive geometry is you can find midpoints, right? If this is point A and this is point B, we can use constructive geometry to find the midpoint of a given pair of points. How do you do it? Well, let me just, before I talk about constructive geometry, how would you do it with analytic geometry? In analytic geometry, you have a coordinate system. You just measure. I go, well, it's 2.5 inches, right? So the midpoint is where? You take 2.5, you divide by what? 2. You get 1.25. So you go, the midpoint, it's right about here. Well, wait a minute. I can't measure. Oh, I can't read. That's 3.5. I'm a dummy. 3.5 inches. What's 3.5 divided by 2? 1.75, right? So like at the 1.75 mark, about right there, is the midpoint. That's how we do it with analytic geometry. We take it for granted, right? You use numbers and division arithmetic to answer these kinds of questions, right? But this would have been distasteful to Euclid. Euclid wanted to not use rulers to do things. He wanted to do everything in terms of basic constructions. And so the way that goes, if I can get my compass to work here. So here's a compass. It's, you know, it's only as useful as it stays put. So here we go. Hopefully it'll behave for me. So what you do is you just sweep out like that. All right, see what I did there? I took from the point B, I swept out a circle. And then here from the point A, I sweep out a circle of the same radius. And then there's going to be a point, see that? Point where those compass lines intersect. Now let me they may not be showing up super great in the overhead. Yeah, they're not. Here, let me just trace where the compass just went. So my pencil mark, I'm just tracing over it, okay? I'm trying to trace over it. Ah, come on. So what's the deal with these marks I just drew? They're equal distance, right? The place where these intersect, they're equal distance from both point A and point B, right? Because they're both on like a circle. So I kept the compass the same size, right? Okay, so you got that point and that point. And then here's the deal. You take those 2 points, right? And then you take your straight edge and you connect those 2 points with this line, which I'll make green. Can you guys tell me what the name of this green line is? So this line is what's called the perpendicular bisector, right? The perpendicular bisector. And where the perpendicular bisector of the line segment AB intersects the line segment AB, this point right here, that's the midpoint, right? So there you go, right there. This is M, midpoint. Of A and B. So there is an example of what's called constructive geometry, all right? And you can go a long ways. Like you can start to, for example, you could start building like ideas of numbers using this geometry. For example, you could think of A as being sort of like, you could think of A as being 0 in some sense, right? And you could think of B as being the number 1 in some sense, right? And if you do think that, then what is the meaning of the midpoint? If A is 0 and B is 1, what's the midpoint? The midpoint you could think of as being 1/2, right? So in this sense, you could use constructive geometry to build numbers. You could construct the number 1/2 as the midpoint. Yeah? And so this, mathematicians from times of antiquity spent a lot of time working on constructive geometry because it was a way they thought they could build number systems and all kinds of other things. And of course, geometry is also just interesting because of its applications to, say architecture and things like that, right? But it turns out that there are limits to constructive geometry. All right, so like, I'll tell you a little bit more. So here's some famous things you cannot do in constructive geometry. So things you can't do. It's too much for this page. I'll go to the next one here, page 2. So, no-go theorems. No-go theorems of constructive geometry. So like one of them is you cannot double a cube. If I remember right. So like if you tried to start with a cube and then imagine using straight edge compass type constructions, you can't create a cube that has double the size. Another one you can't do is you cannot trisect an angle. So, if you wanted to divide an angle into three pieces using straight edge compass constructions, you can't do that. All right, so now how do you prove those things? Well, the answer ultimately comes from like a class here we teach called Math 422. And in there, what is shown is that constructive geometry corresponds to what are called field extensions of even degree. And if you study the idea of doubling a cube or trisecting an angle, it corresponds to a field extension that is not of even degree, therefore it can't possibly arise from constructive geometry. So there's that. All right, let's go on here. So let me get back to the homework if I can find it. Now, how would you can do both of these things with analytic geometry with ease, right? Like you guys, I mean, seriously, like it's not a big deal, right? How would you double a cube? Let me give you a cube. If you're just allowed to use numbers, right? Here, I give you the cube, side length, let's say, well, you pick any side length you want. Let's use side length 3, 3, 3, 3, right? If you want to double, oh, maybe this is a little bit tricky. How would you double the volume? So we're talking about doubling the volume of the cube. If you want a new cube which has double the volume, what would that cube look like? You'd have to have, I'll draw a picture schematically of it. It's still a cube, right? So, oh, that was supposed to be a cube. Sorry, sadness. X, 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 right? The volume is x times length times width times height, right? Which in this case is x cubed. And that's supposed to be twice the volume of the other one, right? What's the volume of my initial cube that we were given here? Volume 3 times 3 times 3, right? So that's 9. 9 times 3 is what? Heart was in the right place, though. Let's see here. So we're supposed to do double the volume, right? So 2 times 27, right? 2 times 27. And you see that would give me x cubed equals to 54. How do you solve x cubed equal to 54? You're like, don't ask me that. The reason I'm not answering that question is I took this class to not answer that question, right? So I hear you. And so I'll do it for you. We take the cube root of both sides. And that's the thing. We get the cube root of 54. So x is equal to the cube root of 54. And 54 is what? It's like 27 times 2, right? So if you take the cube root of that, you've got really 3 times the cube root of 2. So this is the answer to double, basically to double the volume of the cube. You take the length that you're given and you rescale those by just multiplying by the cube root of 2. The thing is, this cube root of 2 involves a degree 3 extension over what are called the rational numbers, and that's not possible using constructive geometry. And therefore, you can't double the cube. This is a little bit more of the details. But you can double the cube if you can just calculate the cube root of 2, which we all can do, right? Because you guys got calculators and stuff, right? How would you trisect an angle? You know, here, if I've got, here's my ray, my angle here is theta. How can I trisect that angle? How do you trisect the angle? This is really profound. Watch me. Theta divide by 3. There you go. I trisected it. All right, so I mean that is literally it. So, and then so you know, in terms of over here, then you've got 2 in between here, and so this is theta over 3. That's theta over 3. That's theta over 3. See, trisecting an angle is not a big deal with analytic geometry, but you can't do that in general in constructive geometry. You can trisect certain special angles in constructive geometry, like maybe you could do something really nice like 90 degrees. Maybe you could construct, there's certain ones you can do. But anyway, enough about this. Let's go on here. So what I'm trying to set the stage here for you guys is to understand a little bit more about the history of all this. So like Euclidean geometry is, thousands of years old. It was the dominant mathematical instruction in like universities and high schools and things like that. People who had the, privilege in their life to get an education and not just, toil away in the farm and not learn anything, that kind of thing. People who actually were able to go on and had enough means for an education, they would learn Euclidean geometry out of these ancient, Greek texts, basically. And that set the stage for like a lot of what was mathematics for quite some time. Now Euclid also studied primes. Like there's a proof in Euclid's Elements that there's infinitely many prime numbers. So that, Euclid also did things with prime numbers. It's not just geometry that he did. But but one of the other things that Euclid did was he had axioms of Euclidean geometry, all right? So like next class we'll probably talk more about those, but I'll just give you a preview. Like the axioms of Euclidean geometry include things like, given 2 points, you can connect them with a line, all right? Another axiom of Euclidean geometry basically says something like, given a line of finite extent, right? You can continue it. You can keep going and going and going and going. It just goes on and on forever. Like lines can be continued to infinity, whatever that means. Another, I'm trying to remember. Another axiom or postulate of Euclidean geometry is that if you have 2 parallel lines, if you have 2 parallel lines, what happens? What do they do? I'll put this on the previous page. So, number 2. And so Euclidean geometry is Euclidean geometry basically is constructive geometry, okay? And another one of those axioms is this result, which is if you have parallel lines, right? What can you say about parallel lines? I think I misspelled that. Feels wrong. I think it was just one L at the end, yeah? Okay, so parallel lines, if they're distinct, right? If you have two lines and they're parallel, what can you say about them? What do they do? They what? They don't touch. And that's the case where you can see them, and it's the case no matter how far out you go, right? So if they're genuinely parallel lines, they do not, and because mathematicians want to be all fancy sounding and, you know, trick people into thinking that they know things other people don't know, we use the word intersect. They do not intersect, right? Which is just a fancy word for touch, right? They do not intersect. So there's tons and tons of work done to try to show that so like mathematicians, they chewed and chewed and chewed on this Euclidean geometry for hundreds and hundreds of years. And one of their big ideas was to try to take that set of axioms that you find in Euclid's Elements and try to like narrow them down and like throw away ones which are redundant, right? Like if you had a set of axioms, they're supposed to be basic truths which cannot be derived from one another. That's kind of the idea, right? So like if you have three axioms, right? Let's say axiom 1, axiom 2, and axiom 3. And then through straightforward logical arguments, you can take axiom 1 and axiom 2 and prove that axiom 3 is a necessary logical consequence. Then mathematical purists would say, well, we should get rid of axiom 3. We don't need that because 3 is automatically following from 1 and 2. So a good set of axioms is kind of minimal, right? It's as small as it can be. And so a lot of people, mathematicians, were of the opinion that this parallel line axiom wasn't needed. Like they thought that that should just be something you could derive from the other axioms, all right? And there is a vast, vast body of work examining how that can or can't be done. And ultimately, looking at that leads us to the topic we'll talk about next time, which is what's called non-Euclidean geometry. In non-Euclidean geometry, one of the things that can happen is that parallel lines might intersect eventually. And if you think about this, you actually already have experience with non-Euclidean geometry. I can't say this in every building, but in this building, if you go out to the big hallway in the front, right, and you look down it, like from the very one end to the very other, like if you think about it, the walls are parallel lines, right? But if you look at it, it looks like they intersect at the end, right? If you just kind of stare down, something like that. So we have, if you think about geometric perception, we have this idea that if you look at things, even lines that are parallel, if they go way, way out into the distance, they appear to what? They appear to intersect, but Okay, enough about that. More on that next time. Let's get back to your homework. How about that, right? So I have worked a few problems in your homework. Is there a particular one you guys would like me to work that I haven't worked yet? No? All right, here, let me talk about this one then. So here's example 1 from today. So we're on page 3. So I'm doing better today. I brought my ruler, so that's good. So you got two lines. I'm going to try to draw them parallel. All right. Come on. And your book calls the one L1. And you label the other one line 2, line 1, line 2, like this. All right, they're supposed to be parallel. And then you've got another line which intersects them, like so. All right. And then what? He labels this angle theta, and we're labeling this angle down here B, and this angle over here A. All right. And so you're given that L1 is parallel to L2, all right? And you're supposed to find the measures of angle A and B when theta is given to be 44 degrees. All right? So there's a theorem of constructive geometry, or anyway, it's a theorem of geometry, let's just say, because I don't want to be. Here's the thing: is Euclidean geometry is actually, as it's practiced, it's actually a mixture, truth be told, of constructive and analytic geometry. So I'm hesitant to call it a theorem of constructive geometry. It's maybe both. Anyway, here we go. So theorem, alternate interior angles for parallel lines are equal. Right, this is a theorem of geometry. So what does this say here? For us, the alternate interior angles are A and theta. So that's what that means. Do you see why I say they're alternate interior? I mean, that's just the name we give them to them. You can see it though, right? That angle A should be equal to the angle theta. Can you see it? All right. And so that means A is equal to what? 44, right? So we got that. Another theorem is that supplementary angles have measures which sum to 180 degrees. So what I'm saying there, what do I mean by supplementary angles? This A and B are supplementary. See that? In the sense that this is B and this is A. So supplementary angles are angles that range over like a straight line like this. Together they go from a straight line to a straight line, like in this sense. Again, let me just say this. I hope you can see it. Please don't make me define it carefully with a sentence. I'll go nuts. All right? Can you see it? They're supplementary. And so this means A plus B is what? 180 degrees. So that gives us that, B is equal to 180 degrees minus A, which, as we just worked out, is 180 degrees minus 44, which means B is equal to 136 degrees. It's a hot one. I'm sorry, that was a horrible dad joke. But I'm a dad, so it's my right. All right, any questions? Yep.
Can you explain the circle question in the homework?
Yes, we can go to the circle question. That would be the kind of question I'm looking for. Circle question. Let's go to that one. So I think we did problems 8 and 9 last time, yeah? Circle questions number 10. So we're on example 2. So you're consider the following. It says when D is equal to 14 feet, so let me write it out. Suppose the diameter of circle is 14 feet. All right, so 14 feet is equal to D. All right. It says give both exact values and approximations to the nearest hundredth. All right. And then the questions are to find the circumference and find the area. All right. So let me just review that stuff here right briefly. So a circle is what? It's the set of points that are equal distance from a central point, right? So you can construct a circle with a compass, right? So that's the set of all points, yeah, that are the same distance from the central point, right? And so we can describe the circle either with what? The radius, right? Radius is the distance from the center. Distance from center to any point on the circle. Or we can define it by the diameter, right? What's the diameter? It's twice the radius, right? So the diameter is the diameter is simply the length of any line which goes through the center of the circle and connects two opposite points, right? Like this. This would be a diameter right here. See that? So here is a diameter. So this distance right there would be d. Okay, so theorem. There are two theorems we should know about for a circle. One is that the circumference is equal to 2 times pi times the radius. All right? And the area is equal to pi times the radius squared, right? Now, of course, what's another formula you could write for the circumference? Since 2 times the radius is the diameter, right? You could also say that the circumference is pi times the diameter, right? So there's that. Now, what's pi? Is equal to 3.1415 blah 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 blah, right? So it's, you know, approximately 22/7. Anyway, so we're supposed to do, what did it say, to the nearest hundredth, right? So let's get our handy dandy calculator out here and do that. By the way, pi is a number that you cannot construct in Euclidean geometry. Pi is an example of what's called a transcendental number. It actually takes rather sophisticated analysis to construct pi. The easiest way to construct pi is as the first real zero of the cosine function divided by 4. Or times 4? Wait a minute, no. Well, times 2 maybe? I'll shut up. All right, let's see here. Pi is, look at this. Look at my calculator. See this? Look at this wise guy. See this? It's like, what's pi? It's pi. Thanks a lot. So if you got a calculator like me, you got to press this S standard. This gives you the decimal for it. But anyway, so pi times what? 14? So 14, thanks calculator. 14 pi is the diameter. I guess it said to give us both. That's all, folks. Let's see here. So the circumference is, yes, it's equal to 14 pi feet. Yeah, 14 pi feet. But that is equal to 43.98 approximately, right? And these are both in feet. Are we good? Excuse me. Yeah. Now to calculate the area, I'm gonna figure out what's the radius. What is the radius here? 7, right? So we take 14 divided by 2 is 7, so we have 7 feet squared. So on the one hand, it's 49 pi feet squared. But if we want to do that carefully, that is 153.94. I got to round that up. That 3/8 rounds up to 4 feet squared. So there it is. Does that help? Okay, cool. Now, you know, if you take the math major, you'll actually derive these formulas in some sense or another, more or less as like a sophomore, somewhere like that. We find some of these things in calculus, actually. We find better understanding of them anyway. Let's go on here. 12, I'll do number 12 next. Actually, let me check myself on the time. We're fine. So example 3. So here I've got some kind of sort of triangle which is tilted a bit like this. All right, and what are we told about this? And this is number... A vegetable garden is in the shape of a triangle with base of 19 feet. So this right here, they tell us is 19 feet. All right, and then if you continue this, ... All right, and you drop that down perpendicularly like this. So they tell us that the base is 19 feet and the height, this is the height, is 17 feet. And then we're asked to find the area of the triangle. So how do you do that? It is 1/2 base times height is the formula for the area of a triangle. So here, that's 1/2 of 19 feet times 17 feet, which is whatever it is. Let's see here. 17 times 19, 323 divided by 2, 161.5 feet squared would be my answer here. Any questions about this? All right. Now we've got something a little bit sneakier. Example, so that was like number 12, roughly speaking. Let me move on to something that's kind of like number 13. So here we've got a building, all right, like this. And so you got some windows. All right, and you're given that this is like level ground. So the building's perpendicular, perpendicular to the, to the ground like that. And the sun is in the sky over here somewhere. Oh man, this is why I don't use yellow. Can you see it? Kind of, sort of, I don't know. Anyway, there's a shadow, right? Shadow, which I'll use green for because why not? And so anyway, the sunlight makes a shadow like this. It's a shadow. And we're given, well, let's say that the shadow has length d, all right? And on the other hand, you have maybe a light pole over here, right? And my picture is really not quite right, is it? Because the sun is the sun right there? It's not, right? The sun is actually really, really, really far away. So for all intents and purposes, the light ray from the sun come in parallel to the edge of the building and to the edge of the light pole, right? So what that means is that this triangle, the triangle that's formed by the building and the triangle that's formed by the light pole here, they're similar triangles. What are similar triangles? So similar triangles share same angles, but may have differing side lengths. Another way to say that is this. The ratio of corresponding sides of similar triangles are equal, all right? If you match up the sides appropriately. Another way to say this is similar triangles. How can you get from one similar triangle to another? Remember last class I took the 3, 4, 5 triangle and I multiplied it by 2 and then I multiplied it by 13, you remember that? Those are examples of similar triangles because one is just a rescaling of the other. In the same sense, the triangle formed by the light pole and the triangle formed by the building, they're similar triangles. There's one's just a blow up of the other. In contrast, you can talk about congruent triangles. What's that? This is not for this example so much, but just while we're at it, congruent, on the other hand, means something different. Congruent means same lengths and angles. So congruent triangles are, like here is an example of congruent triangles. Check this out, right? If I have, say this, see which one I'm using here? This guy? That triangle. And then I go over here, I rotate like this. And then I go over it. Once you get started, you can't stop, like this. And then like this. See these? These are all congruent. They're not the same place, right? But you can move one congruent triangle to another by what's called a rigid motion. You can like shift it to the center of the other one and then rotate to make it match up. These triangles are congruent. In contrast, the triangles I'm about to shade in, if I can find my gray. Where's my gray? Oh man. Ah, in the box. In contrast, these two triangles here, see this one? And this one, they're not congruent, right? But they are similar. All right, so let's get to the point. You're given that the shadow has length 4. And this one's in meters. Proper European problem, there you go. 4 meters. And you're also given that x is equal to 2 meters. And you're given that this y is equal to 4 meters. I guess it's kind of that's reasonable. It's about 15 feet high. There's a lot of light poles like that, right? And so we have and so we're trying to find out what's the height here is really the question, right? So that's this distance, right? What's the height? So here's the way it works. The height divided by 4 meters, right, should be equal to the y over x. See, that's what I'm doing is this is the similar triangles. The ratio of matching sides of similar triangles has to be equal, right? Now you can solve that. We don't know h, right? So solve for h. Can you guys do it? What we get? All right, so that gives us h is equal to 4 times 4 over 2, right? And I guess I can put the meters in. Meters, 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 2 meters. You see the meters cancel, and you're left with 16 over 2, which is 8 meters. So there you go. The building is 8 meters high. So you can use this trick, right, to estimate like the height of a mountain or something, right? If you're in a plane, and at the time of the day, the mountain comes in, and the shadow of the mountain, you can see where it hits the plane, right? If you also have a pole in the plane that you have a known height and you can measure the length of its shadow, then you can extrapolate how high the mountain is, right? So that's kind of neat, because that means you can measure the heights of things that you can't climb even, right? Because you don't actually have to go to the top of the building and make this measurement. You just have to measure the light pole. It's pretty neat. All right, example where are we? Example 5. Here we're given two triangles, all right? So I'm going to freehand it here because and so these pictures, you're not supposed to like use the picture how it looks necessarily. In these kind of pictures, the picture may or may not actually be accurate to the actual lengths given. So I've got this triangle, and I've got this other triangle over here, D. So we can refer to a triangle by its vertices, right? So like the one is the ABC triangle, the other one here is the DEF triangle, yeah? All right, and this is 5 inches here. And then the question is, determine whether the two triangles are congruent. If they are congruent, state by what theorem? So I should probably state that theorem, huh? So theorem, two triangles are congruent if they have matching, and here's the typical nomenclature used, either number 1, side, 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 or 2, side, angle, side, or 3, angle, side, angle. Fortunately for us, another option is not realized. Let's see here. Got to know your audience. Let's see here. I was not saying that. That was not what I meant. I'm so sorry. Let's go on here. Moving along, 5, 6. All right, so what this means is that either you have to have, like if you have two triangles, like let me show you examples of this, right? If I have, and if I have these two triangles like this, 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 right? And this is 3, this is 3, and this is 2, and this is 3, and this is 3, and this is 2, then I could say, hey, those two triangles are congruent by side, side, side. They have 3 matching sides, right? So these two are congruent by the side, side, side theorem, right? All right, so how about the problem which is given here? And this is, by the way, number 14 in your homework. So you guys tell me, what do you think? Are these congruent? Are they not? Yes, and by what? Congruent by what? By side, angle, side. Yeah. So side, angle, side, what this means, there's something kind of loaded in the notation. Side, angle, side means that angle is the one that's between the sides. Right? So like it has to be the angle which is nestled between the two sides. See that? So here, this side we could think of as the 4-inch, right? This is the 47 degrees, and that's the 5 inches. All right? So yes, it's congruent by side, angle, side. The thing that's kind of funny about this, right? And the thing is, over here, I neglected, you're like, well, you didn't write the problem down yet, mister. True enough, they were supposed to write 4 inches here. If you were confused up to that point, good. So we have to have the 4 matches the 4, the 5 matches the 5, and the 47 is the angle between them, right? The thing is, if one of these is true, the other two are also true, right? Because if the two triangles are congruent, it's also true that the missing third side is also the same length. We don't know what it is, right? But it is true. The unlabeled side length, whatever it is, it has to be the same. Because if they're congruent, then all these things are true. Side matches, side matches, side, side angle, side matches, and angle, side angle matches. Yeah. But anyway, the answer here was yes, it's congruent by SAS theorem. All right. How would you find the length of the other side there? Pythagorean theorem, not quite work here because it's not a right angle. The answer is relax. That's not a question I ask you in this course. All right, so the answer is we have to do more with angles, and we need trigonometry to answer that question. Is the quick answer there? And so I didn't want to put sine and cosine into this course because I think that's kind of a bit much for Math 115. I thought about it. I almost did it, and then I was like, well, let's not do that. I don't want to be mean to you guys. Let's see here. So here we've got A, we've got C, we've got B, and then let's see here. Over there, I've got a picture like this. I'm drawing it as best as I can, guys. So they label X miles here and Y miles there. And they also tell us that this, I regret not drawing these triangles bigger. This here, sorry about this, guys. This angle is C degrees. And this angle over here is A degrees. And this angle here is D degrees. And this angle here is F degrees. All right. And the label on the triangle, come on. Over here we've got F, D upstairs, E over here. All right. Now here's the question. You determine whether the two triangles are congruent. If they are congruent, state by what theorem. All right. And here what we're given. We're given the following. A is equal to 115. I'm going to say degrees. Let's see here. C is equal to 40 degrees. F is equal to 40 degrees. And Y is equal to 4 miles. X is also equal to 4 miles. I think I missed something. What was D degrees equal to? D is equal to 115 degrees. So what do you guys think? Congruent? So we've got the F is 40 degrees, and C is 40 degrees, D is 115, A is 115. So I believe this would give us, it's congruent by what? Angle, side, angle, this one, right? This is congruent by angle, side, angle, because you're matching up angle with angle and side with side in the same way on both triangles. So it's congruent by angle, side, angle. This was number 15. Now, one of you asked about Pythagorean theorem. Let's do that one, yeah? What is the Pythagorean theorem? So here we go. This is really just a plain old simple Pythagorean theorem problem. Number 16. So here we go. We've got a right. So Pythagorean theorem is true for right triangles. All right. So I've got this here right triangle. What is a right triangle? What's that mean? That means one of the angles is what? 90 degrees, right? What do you say about a triangle